Hi students, today we will discuss about double integration. So very interesting topic. So first of all we will know about integration. So what is integration? So integration is what? It gives the area under the curve. So which means that, for suppose if a curve is like this, so we need to find the area under this curve. If it is a continuous curve, just maybe like this. The process of finding this area under the curve is called the integration. We need to find this area. So this is what? An integration. Now, so please observe this, how to find the area under this curve. So clearly, so we will find the area of rectangle by using a formula L into B. Circle pi r square. Square, no problem. Side square. So all these structures have formulas, but so how to find the area under the curve? So this is a very important one. Now, so what I am trying to do is, for suppose it is a curve and we need to find the area under this curve. See, so I make this curve into small rectangular pieces like this. Very small. So like this. So we have some infinite number of rectangular boxes are there. Now, after finding the areas of all these rectangular boxes, while adding all these rectangular boxes, what will get? Area under this curve. So please see this. So we have infinite number of rectangular boxes. While combine all these rectangular boxes together, then what will get? Area under the curve. So that the process of finding the area under the curve is called the integration, which means that some of the small pieces under the given curve. So clearly, so which means what? Now for suppose if it is f of x, given curve which is known as y equal to f of x. Now the width of the length or breadth, whatever it may be, the rectangular box is, for suppose, delta x, and for this the height is what? F of x. Y means it is in the y. So the length is delta x and the height is f of x. Now what is the area of this rectangular box? So area of this rectangular box, for suppose, so rectangular box should be like this, and so it is delta x, and what is the height, what is the length, which is nothing but f of x. So clearly all with this for these rectangular boxes are same and which are very closer. Now what is the area of this rectangular box? Length into breadth, which means what? F of x into delta x. So clearly area of this rectangular box is what? Length into breadth. Now how many rectangular boxes we have? Some infinite numbers are there. So which means that clearly as delta x is very closer to 0, approaches to 0, so width is very lesser, which is approaches to 0, and adding all the rectangular boxes, which gives the area under the curve. Why? Because while you add all these rectangular boxes, what we get? Area under the curve. See, adding all these rectangle boxes, area under the curve. So A is what? Which means that how to find the area? Adding all the areas of these rectangular boxes, which means that summation of, so all are having lengths and breadths are same, which is known as f of x into d of x dx. So clearly summation, which is known as, what is this summation? Clearly this is what? Sum of small spaces under the curve. Sum of small spaces under the curve. Small spaces, areas of the small spaces is what? F of x into dx. Clearly, so all these rectangular boxes having the area, so with respect to the x value, so here f of x into dx. So clearly sum of small pieces under the curve. Now sum is nothing but addition. So clearly I take sigma is a sum which is known as prolongated S. So what it indicates? Sum, prolongated S, sum of small pieces under the given function. So which is known as sum of all the areas of the rectangular boxes, which gives the area under the curve. So this is what? How to find the area under the curve. So clearly this is the process of finding the area under the curve. Now, so coming to the volume, so coming to the double integration. So integration is what? Process of finding the area under the curve. So coming to the double integration, the process of finding the volume under the surface. So clearly double integration what? Is process of finding the volume under the surface is what? Double integration. So here we have a unspecified figure here. We need to find the volume under this surface. So under this surface clearly, so that how to find the volume under the surface. See, it is all about 3D, three-dimensional. Now we need to find the volume. So volume is what? For suppose, if what is the area of the rectangle? Length into breadth. Then coming to the, this is the area. Then what is volume of the cuboid? Length into breadth into height. So area into height is what? The volume. So area into another third dimension, which gives the volume. So volume of the space. So particular object. Now coming to finding the volume of the particular object. Now I need to find the, so area of the particular surface and then volume. So now I have to consider the surface OABC from this figure. See, so from this surface I need to find surface OABC. So OABC clearly, so OABC completely lies on the ZX plane. So ZX plane. So clearly, so this is the structure which is represented by Z equal to f of x comma y. Okay, now I need to take a surface. So I want to find the area of the surface and then volume. Now in the ZX plane, zx. So now the surface OABC O, A, B and C. So now I need to find the area for this. So how to find the area of this unspecified object? So clearly, so first one is make them into a small pieces, rectangular boxes. So clearly, partitions. Small rectangular boxes. So width of the small rectangular box is what? Delta x. And what about the length? Z. Now clearly, now so take this one, take this rectangular box. So what is the width? Is dx and the height is what? Z, which means, so here the function is z in terms of x and y. So okay, now what is the area of this rectangular box? Is a equal to length into breadth, which is what? Z into dx. Now as dx is very closer to 0, now while adding all the rectangular boxes, which gives the area under the surface. So as dx is very smaller, which is approaches to 0, then while adding all these rectangular boxes, which gives the area under the surface. So that the while adding means summation, so that I need to find the area. So area of plane OABC equal to what? Summation of all these rectangular boxes, so which is nothing but sigma z into dx. Now summation. So summation is what? So prolongated s, which is nothing but integration of z into dx. Okay, then so from this, now I have an area that is the integration of z into dx, and we need to find the volume. So that how to find the volume of under this surface is, so this is the volume of this surface. Now so finding the total volume is not possible, that's why I make this into a small pieces, like so make this small pieces. So this is the part, so this is the part I need to take. So that, see here, so this one clearly, it is like this. After finding this, so while adding all these volumes, which gives the entire volume of the surface. So first my intention is finding the volume of the first this surface. After adding all the volumes of this surface, which gives the entire surface volume under this entire surface. Okay, now I want to find the volume of first this surface. Okay, now so clearly for this surface, so this side or this side, whatever it may be, so what is the area of the surface is integration of z into dx. So clearly, so this is what? Integration of z into dx. Now see here, the width is what? here dy, so which represents the y-axis. So width, so clearly it represents the y-axis, so that so I make a small piece, so the width is what, dy. Now here dy. Now so what is the volume of this space, slice, whatever maybe, is nothing but area into, so another dimension, so area into another dimension. So area is what, integration of z into dx into the another dimension is dy. So now, so this is the volume of this one slice. Now we, how many slices we have under this surface? Some infinite number of slices are there. So as so dy approaches to 0, so as dy approaches to 0, so while adding all the volumes under this surface, all the slices under this surface, which gives the volume of the entire surface. So now what I am trying to do is, we need to find the volume of under this surface, so that volume under the surface is equal to, so summation, sum of all the small slices, so which is what, so yes, integration of z into dx into dy. So here what is the meaning of summation? So prolongate is, which means what, so prolongate is integration of z into dx into dy. So this is what, volume under the surface. How to find the volume under the surface? So double integral of z in dx into, so dy, which is what, integration of z is what here, function in terms of x and y into dx to dy. So now you please see this. So I have taken a, so rectangular box, so having, so x, y, z, now see this. So how to find the area of this, so how to find the volume of this rectangular box? So clearly, so we have double integration, see, so from this integration of a to b, function in terms of x and y dx, and integration of c to d into dy. So this is what we need to find the volume under the surface. See, so here, so if we need to integrate with respect to x, then treat y as a constant clearly. So after finding the integration for this, so we need to find the integration with respect to y. So first thing is, so if you want to find the integration for this, treat y as a constant and then integrate the entire value with respect to y. So okay, here the order of the integration, so does not matters, so which means that, so we need to change like this. Which is also be known as so integration of a to b, c to d, dy into dx. We can write like this also. So here, so what we observe, the order of the integration, so does not matter. So clearly order is interchangeable. So this is the very important thing. So we solve one problem from this. Then we will get a complete idea about this double integration. So for suppose integration of 1 to 3 and integration of 0 to 1 plus 4xy, so dx dy. Now, so first thing is with respect to dx and then dy. Now, so if you want to integrate this, treat y as a constant. Now I will write like this. So integration of 1 to 3 to dy. Now in between them, so we have integration of 0 to 1 plus 4xy into dx. See, now finding the integration for this. So integration of 1 to 3 of, so integration of 1, so with respect to x, which results to x plus, so 4y is a constant, so 4y is a constant, and the integration for x is x square by 2. The boundaries are 0 to 1 and dy. So now, so substituting the boundaries, so for upper boundary, so 2 1s are 2 2s gets cancelled. Now it is what, x plus 2yx square, the boundaries are 0 to 1, and in between them we have dy, integration of 1 to 3. So see, so integration of 1 to 3, so in between them, finding the upper boundary, so substitute 1 plus 2y into 1 is 2y, so over, so minus of, now substituting the lower boundary, 0 plus 0 is what, 0 clearly, so over. Now what we get finally, 1 plus 2y. See, the remaining thing is integration of 1 to 3, 1 plus 2y dy. Clearly, so for 1 we have y plus 2y we have y square, and the boundaries are 1 to 3. Now substituting the boundaries, for upper boundary 3 plus 9, and coming to the lower boundary 1 plus 1. So 3 plus 9 is what, 12 minus 2, which is what, 10. Now, so I'm interchanging the boundaries, so which gives, so integration of 0 to 1 and integration of 1 to 3, so 1 plus 4xy to dy to dx. See, integration of 0 to 1, and for this, if you want to integrate with respect to y, so treat x as a constant, and for this 1 we have y plus 4x into, for y it is y square by 2, and the boundaries are 1 to 3, so it is dx. Now 2 1s are 2 2s gets cancelled, so it is 0 to 1. Now substituting the boundaries for this, plus 2x y square 3 dx. Now 0 to 1. Now first upper boundary, now so upper boundary, what we get, 3 plus, in place of y, So 3 square is what? 9. 18x plus 18x minus, coming to the lower boundary, 1 plus 2x. Now see, integration of 0 to 1. Finally what we have? 2 plus 16x 2dx. So now we need to integrate with respect to x. So finally what we get? For 2 we have 2x, integration is 2x plus 16 into, for x square by 2, and the boundaries are 0 to 1. So 2 1s are 2 8s are. So now substituting the boundaries, 2x plus 8x square, the boundaries are 0 to 1. Now substitute the upper boundary, what we get? 2 plus 8, and coming to the lower boundary, 0 plus 0. So what we get finally? It is 10. Now, so before interchanging the boundaries, what we get? 10. After interchanging the limits, so boundaries, what we get? 10. So that order is, so boundaries order is interchangeable, no problem. Now, so clearly here the one important thing is, so bounds of first integration can be in terms of other variable. In the next video we will discuss about this. So this is the very important one. Bounds of the first integration can be in terms of other variable. So can be in terms of other variable, and the bounds of, so second integration must be in terms of numbers, which is constants. So this is the very important one. So the bounds of the first integration can be in terms of other variable, so maybe in terms of other variable or should be constants, but the bounds of the second integration must be in terms of numbers. So you please see this. For suppose the problem just like this, 0 to 2. So bounds of the second integration must be in numbers, and the first integration is what? X square 2x, and the function is f of x comma y dy to dx. So should be like this. Now in the next video, so we will discuss about it clearly. See, so the bounds of the first integration can be in terms of other variable. So this, so we need to integrate with respect to y, but the boundaries are other variables, x square and 2x, and the bounds of the second integration are constants. So we will discuss it in the next video. Thank you, students.